Hi everyone, my name is Shanya Yang. Today I'm going to present our paper, ALDA, Using Edges to Have an Edge on Semantic Segmentation-Based UDA. Supervised learning for semantic segmentation has achieved remarkable success in the past few years. However, training the model in a supervised manner requires pixel-level labeling data, and collecting label data is expensive and time-consuming. Being aware of these drawbacks, recent research has been trying to use the existing label data to train models, and then adapt the model to label-less target domains. These categories of research called unsupervised domain adaptation, abbreviated as UDA. UDA can bridge the discrepancies between different domains, and a number of approaches have been explored to tackle this challenge. A few research adapted adversarial training process to learn representation of their target domains, and another line of work focused on self-training and data augmentation measures to tackle UDA problems. However, these methods only rely on semantic labels in the source domain and the raw input data in the target domain, which limits their performance and thus leaves room for further improvements. To further improve the performance, another branch of work has incorporated domain-invariant information into their training process. Domain-invariant information represents the concept which is general across different domains, and this property makes it highly desirable for UDA tasks. A commonly adapted type of domain-invariant information is depth, which contains clues relating to distance of the surface of seen objects from a viewpoint. For example, CUDA exploits a segmentation path and a depth estimation path in their UDA framework. CUDA further uses more auxiliary paths, including depth estimation, surface normal, as well as self-supervised photometric rules in their UDA model. Unfortunately, using depth information have two crucial constraints. First, the computational cost associated with training an accurate auxiliary depth estimation model is often expensive. Second, since self-supervised learning-based models have no access to ground truth labels, their performance is not comparable to physical sensors. In other words, their predictions might be off from ground truth and cause negative impacts on the training process. Therefore, we propose to replace depth with edges, which is also a type of domain-invariant information. The benefits are twofold. First, the computational cost of extracting edges from an input image is lower than those of extracting a depth map using self-supervised learning. Second, the quality of edges is typically much more consistent than that of depth maps. In order to take full advantage of edge information, we propose edge learning-based domain adaptation, abbreviated as ALDA. ALDA utilizes edges as domain-invariant information by incorporating edge extraction into its training process as an auxiliary text. This figure illustrates an overview of the proposed ALDA framework. Our framework is mainly composed by three components, including shared domain-invariant encoder, text-specific branch, and correlation module. Later, I will explain our architecture components one by one. First, an input image from either the source domain or the target domain is fed into a shared domain-invariant encoder to obtain shared latent feature embedding. In auxiliary text learning, this step can extract common features so as to enhance performance and reduce inference cost. Later, two separate branches of text-specific branches are utilized to generate initial edge and segmentation predictions. The encoders are in charge of encrypting shared features into text-specific features, which are later fed to the correlation module. Meanwhile, the decoders are employed to decode edge features and semantic segmentation features to edge predictions and semantic segmentation predictions respectively, for updating shared domain invariant encoder and text-specific branches. Lastly, in order to communicate information between edge features and semantic segmentation features, we employ a correlation module into LDAP. By reweighting the text-specific intermediate embeddings, correlation module assists in preserving the essential features from both text-specific branches. In LDAP, the total loss can be formulated as edge estimation loss plus semantic segmentation loss. For loss function for edge estimation, the supervision targets for edges in both the source and the target domains are generated using the K-NIN edge extraction algorithm. An edge loss is then computed between the edge prediction from LDAP and the edge generated by K-NIN algorithm. On the other hand, for the loss function for semantic segmentation, the training targets in the source domain are the ground truth labels, while those in the target domain are pseudo-labels generated using LDAP's predictions. Then the loss is computed between the prediction of LDAP and the training targets by using cross-entropy operator. We then evaluate and compare the experimental results of LDAP against the pure semantic segmentation-based UDM method, as well as methods that take advantage of additional information in the form of auxiliary text. We evaluate LDAP and the baseline on GTF5 to Cityscape benchmark and Cynthia to Cityscape benchmark. These are two commonly used benchmarks for evaluating UDM model. This table compares the results of LDAP against multiple baselines on the GTF5 to Cityscape benchmark. By leveraging edge prediction as an auxiliary text, LDAP achieves an MIOU of 57.3%, outperforming source only by a margin of 20% MIOU. And the results on the Cynthia to Cityscape benchmark display a similar trend as those on the GTF5 to Cityscape benchmark. In this benchmark, the depth ground truth labels in the source domain are provided and are leveraged by a few baselines. In contrast, LDAP is able to achieve superior performance without the use of any extra labeled data. We further selected some images to present qualitative results on the GTF5 to Cityscape benchmark. The incorporation of edge information allows LDAP to even capture small features of the image, like the hollowness at the center of bike wheels. In contrast, the predictions from CRODA fail to capture a similar degree of details, which is due to the use of relatively ambiguous depth information during its training process. Because LDAP is made out of multiple key components, we do the ablation analysis for validating the effectiveness of each component. The experimental results show that with the addition of each component, the performance grows, indicating that the adoption of these components in LDAP indeed has positive performance impacts. In addition, to verify that LDAP is able to learn a more discriminative and thus descriptive feature space, we visualize the target domain features using T-distributed stochastic neighbor embedding. It is observed that the target domain features captured by source only does not have clear boundaries between different classes. In contrast, the features captured by LDAP display clear boundaries, translating to the superior performance in the target domain. In summary, we propose a framework LDAP for performing semantic segmentation-based UDA. We use edge information as the domain-invariant information and achieve outstanding results on two commonly adapted benchmarks. Finally, we present an ablation study and feature analysis in the target domain to validate our design choices. This is the end of my presentation. Thank you.